Alright, we have our first Mastering Physics assignment here, and the first problem is about a racquetball hitting the wall with a speed of 30 meters per second, and it rebounds in the opposite direction with a speed of 26 meters per second. So, that's an important thing to keep in mind. Initially, it's going in one direction, could be to the right, we don't know that for sure, at 30, and then it rebounds going at 26 in the opposite direction. So to find our acceleration, we're going to be thinking about our equation for solving for the acceleration, of course. And so I'm going to start by thinking about the things I know. So I know my initial velocity here is 30 meters per second. I know my final velocity after it rebounds is 26 meters per second, but I need to make sure I put a negative sign here because that direction is opposite the initial direction. I also given my time here. It says the collision lasts for 20 milliseconds, and I know that 1 millisecond is 10 to the negative third seconds, so my time actually ends up being 0.02 seconds. So now I can go ahead and plug that in. So I'm going to say my acceleration is equal to my final velocity, negative 26, minus my initial velocity, which is 30, all over my time, 0.02. And so I get an acceleration here of negative 2,800 meters per second squared. So this is probably just looking for the magnitude. It doesn't specify that. But depending on which direction you said was negative, okay, you could have flipped these two. You would get the positive answer. But the answer is going to be 2,800, at least for the numbers that I have. All right, so moving on to the next one, it's yet another acceleration problem. So we have our acceleration formula, Vf minus Vi over t. And we're going to think about the things that we know. So I know that my initial velocity here is 60 kilometers per hour. But we want to go ahead and convert that into meters per second. So we're going to say that 1 hour is 3,600 seconds. Okay, gets rid of hours. And then we're going to go from kilometers to meters. So we're going to say 1 kilometer is 10 to the third, or 1,000 meters. That gets rid of kilometers. And now we have a velocity in meters per second. So we end up with 16.67 meters per second. And we're going to do the same thing for our final velocity here, 90 kilometers per hour. We're going to convert that. And so we get a final velocity here of 25 meters per second. The other thing that we know is we also know that our acceleration is 2 meters per second squared. So I'm going to go ahead and fill in the things I know. So I'm going to say that 2 is equal to my final, 25, minus my initial, 16.67, all over my time. So 2 is going to be equal to 8.33 over t. And I can go ahead then and solve for t. And so I end up getting a time here of 4.17 seconds, which would round, if we're doing 2 sig figs, to 4.2 seconds. Up next here, we're talking about a train that's accelerating while going through 2 cities. So initially we have this part where the train is traveling through a congested area at 7 meters per second, and then it's going to speed up. So that's the first acceleration. And so what we know for that one, we know initially we're traveling at 7 meters per second. Our final velocity after speeding up is 14 meters per second. And the time it takes for that acceleration to occur is 8 seconds. So before I go on and really worry about what I'm actually looking for here, I'm going to use what I have and find whatever I can find. So acceleration is v final minus v initial over t. So I can say that my acceleration is going to be 14 minus 7 all over my time, which is 8 seconds. So my acceleration here ends up being 0.875 meters per second squared. After it reaches that speed of 14 meters per second, there is a second acceleration that it talks about here, speeding up again on the edge of town for 16 seconds. So I'm going to set up what I know for that. I know that my initial velocity now has become 14 meters per second because it's already traveling at 14 when it undergoes the second acceleration. My acceleration is the same, 0.75 meters per second squared. And my time here is now 16 seconds, so I want to solve for my final velocity. So same setup here, acceleration is Vf minus Vi over t. I have this is 0.875 equals Vf minus 14 over 16. If I were you, I would go ahead and cross multiply here. And so what I end up getting is 14 is equal to, that's why I multiply the 0.875 by 16, is equal to V final minus 14. So my final velocity ends up becoming 28 meters per second. Alright, for this next one we have a runner going around a track. So the track consists of two parallel lines that are each 96 meters long. Okay, and they're connected by semicircles on the curves, each one with a radius of 49 meters. So something like this. And so we have a runner here that completes one lap, so starting here, running all the way around in 100 seconds, and we want to know the average velocity of that runner. Okay, well, all we have to really think about is what is our displacement. We start here, we end here. Our displacement is 0 because we are 0 meters from where we started. Therefore, our average speed is also, or average velocity is also 0. Average speed, on the other hand, would be different because then we would care about the distance. We would actually have to go through and solve for that. But luckily, we don't have to do that here. We just need to know that our displacement is 0. All right. Moving on to our next one, we have an 8-kilometer long race, and we have two different runners here. So I'm going to make two charts, one for each runner. So runner 1 and runner 2. And we know that runner 1 runs at a speed of 11.6 kilometers per hour. And runner 2 is going to be running at a speed of 14.9 kilometers per hour. So how they phrase this question is going to be really important. It asks us how far from the finish line is the slower runner when the faster runner finishes the race. So that means the distance for the faster runner is 8 kilometers. And if we know that distance, we can solve for the time. I'm not going to bother to convert here because I notice that my final answer needs to be in kilometers. So I'm just going to leave my speed in kilometers per hour and leave my time in hours. Okay, so average speed is distance over time. So we have 14.9 equals 8 over t. I'm going to go ahead and cross multiply here. What I end up getting is 14.9 t equals 8. And so my time here is going to be 0.54 hours. Now, that time, all right, because we're worried about where the slower runner is when the faster runner finishes, that time also happens to be the time that the slower runner is running. We want to know how much really of the race has the slower runner completed when the faster runner finishes. So I'm going to then go ahead and set up another chart here, set up another equation. So we have 11.6 equals the distance over 0.54. Okay. And so I multiply this by the 11.6, and I end up getting a distance here of 6.23 kilometers. I should note real quick that when I am using a time like this, I'm actually in the calculator using the unrounded value. That's usually a good idea because with mastering physics, it does try and you have to be within a certain tolerance. So I'm really using this number even though I'm writing down 0.54. So what is my final answer here? Okay, well, the slower runner has run 6.23 kilometers of the full 8-kilometer race in this time, which means the part that's remaining right here is going to be 1.77 kilometers. So that's going to be our final answer, at least for these numbers. Alright, so next we have a problem here about a motorist who travels 160 kilometers at 80 miles per hour and 160 kilometers at 100. This one's actually very similar to what we did in class, so you guys should be good on doing a problem like this, but we'll set it up anyway. For the first part of the trip, we know that the average speed here is going to be 80 kilometers per hour. And we know our distance is going to be 160 kilometers. Yet again, because my final answers here are all in kilometers per hour, I see, I'm going to go ahead and leave this in kilometers and kilometers per hour rather than converting it. So I can set up my good old equation here. Speed, average speed that is distance over time. So I can say 80 is going to be equal to my distance, which is 160 over t. Cross multiply once again, and I get 80t equals 160. So that means that t is going to be 2 hours based off of the units that I used. I should have put the subscript here, T1, so that we know we're talking about the time for the first part. Moving on to the second part here, we know that our average speed for this part is 100 kilometers per hour. Okay, our distance is still 160 kilometers. And now I can go ahead and solve for my time. So we're going to use our average speed equation yet again. So I'm going to say 100 equals 160 over t. And now our time here, when I go ahead and cross multiply, is going to be 160 over 100, or 1.6 hours. And we'll call this one T2, the time for the second part. And now we're going to go ahead and do our total. So we know our total distance here because it's two 160 kilometer trips, so it's going to be 320 kilometers is the total distance traveled. Our total time is going to be the sum of the two times, so 2 plus 1.6, which is equal to 3.6 hours. And now we can go ahead and get our overall average speed. So that's going to be distance, 320, over our time, 3.6. So when I go ahead and do all that, again, average speed here of 88.9 kilometers per hour. Now this makes sense because it's a little bit less than 90 kilometers per hour, which would be directly in between the two, and that's simply because we spend a little bit more time at that 80 than we do at the 100. So our final answer is going to be that 89 kilometers per hour, just under, right in between. Okay, moving on to our next problem here. So this once again is a problem where we have multiple parts. We have the first part, we have the second part, and we have the total trip. So I'm going to start with the things I know about the first part. I know that my speed for the first part is 80 kilometers per hour, and my time is 3 hours. I don't know my distance, but I can go ahead and solve that using our average speed equation. The average speed is distance over time. So 80 is equal to distance over 3, which means that my distance here is going to be 240, and it's going to be in kilometers because my time was in hours and my speed was in kilometers per hour. Moving on to the second part, I know that my speed is 100 and my time is 2 hours. I don't know what my distance is, but I can go ahead and solve for that. So average speed, once again, is distance over time. So I can say 100 equals my distance over 2, so my distance for the second part is 200 kilometers. Now that I have those first two parts, I can use that information to get the distance and time for my total. So my total time is going to be 5 hours, the sum of the two times for part 1 and part 2. And my total distance is going to be 440 kilometers, the sum of the two distances for part 1 and part 2. So my average speed then, once again doing distance over time, is simply going to be 440 over that time of 5 hours, and so I get an average speed here of 88 kilometers per hour, almost halfway between 80 and 100, but closer to the 80 because we spend more time at that speed. Okay, moving on to this next problem. Here's one where I think drawing a picture would be useful because we have some information about the path that a person, John, walks. So John walks 2 kilometers north, so that's going to look something like that, starting from here. And then he turns right and walks 2 kilometers east. and ends at this point here. So the first question is, what is the magnitude of his displacement, which, remember, is the distance from where he started to where he finished. So in order to get that, I'm going to use our trusty Pythagorean theorem and get that hypotenuse. So when I do that, 2 squared plus 2 squared equals c squared, I get a hypotenuse here of 2.83, and the answer is going to be in kilometers because that was the distance for each of the sides. So there's that first answer. So for the second part, we have another person, Jane. All right, so I'm going to write down the things that we know about Jane, who starts at the same time and place as John, but walks in a straight line to the endpoint of John's stroll. And we want to know what speed she should walk at to arrive at the endpoint at the same time as John. So we're looking for her average speed. We know, though, that her distance that she walks is going to be this straight line here. So we found that answer in the first part. That's going to be 2.83 kilometers per hour. Okay. So in order to figure out that speed, we simply need to know the time. So what we're going to do is we're going to look over here at the information we know about John, and that's going to allow us to find the time. So we know that John walks at an average speed of 1.4 meters per second. And we know the distance he walks is 4 kilometers. Two important things about that. Number one, I realized we just calculated John's displacement here, but we don't know his average velocity. What we do know is his average speed. And if we're using average speed, we have to use the distance, the actual distance he traveled, which is 4. Something else, though, is we want to go ahead and convert this. We want to go from kilometers to meters, and so we end up getting a distance here of 4,000 meters. So we can go ahead and set this up now to solve for time. Okay, we can say our speed is distance over time. So we have 1.4 equals 4,000 over t. And then we can say 1.4 t equals 4,000. So our time here is going to be 2,857 seconds. So that's going to be the same time we're going to use here for Jane. We do, though, need to convert this 2.83 kilometers, so I'm just going to do that over here. We know 1 kilometer is 1,000 meters, and so we get 2,830 meters is the distance Jane walks. So now we can go ahead and use my speed equation with the information for Jane. So I'm looking for her average speed. The distance she travels is 2,830 kilometers, and it's going to take her 2,857 seconds. And so when I go ahead and calculate her speed, I get an average speed of 0.991 meters per second. All right, moving on to the final problem here. We have a strobe diagram here showing the motion of a ball. One really important thing to note is that this was made at 2 frames per second, so that means that each time we go 2 frames, that's 1 second. So there's 1, there's 2, there's 3. So this first question is just asking about what is the change in the ball's position from 0 seconds to 1 second. So that's going from here, there's half a second, there's a full second. So the change in position or the displacement is just going to be 4 meters because we go from -4 to 0. All right, moving on to part B. What is the change in the ball's position from 2 seconds to 4 seconds? Well, like we said, each one is 1 second, or every 2 dots is 1 second. So there's 1 second, there's 2, there's 3, 4 would be that final frame there. So going from 2 seconds to 4 seconds, we go from 3 to 4, or 3 to 7, which is a displacement there of 4 meters. Part C, what is the ball's velocity before reaching the sticky section? So that's right in here. And we know that during that time, our displacement was 4 meters and our time was 1 second. So we have 4 meters over 1 second, or 4 meters per second. That's going to be our velocity during that period of time. It does ask for 2 significant figures, so 4.0 in this. And then for our final one, part D here, same idea. We want our displacement during that part after the sticky section right in here. And so our average velocity is going to be our displacement there, 4 over our time, which is 2 seconds, and we end up with 2.0 meters per second. All right, for the last part, we want to determine the ball's acceleration on the sticky section of the track. We know the acceleration is v final minus v initial over t. From the previous few questions, we know that our final velocity after the sticky section is 2 meters per second. Our initial velocity before the sticky section is 4 meters per second. And our time here is going to be 1 second because the sticky section takes up 2 frames. So we can go ahead and plug in those values here. Be careful, our final velocity is less than our initial. So that means that we should get a negative acceleration, and if you don't put that in, you will get the answer wrong. But we should end up getting an answer here of 2 meters per second squared.